Hello guys, so this is lecture 5.3 and this lecture is about roots of unity. So if you have never heard about that, even the name roots of unity might sound strange because, unity. Because what is the square root of unity, right? So obviously 1. So the answer is that even that is not very clear because there is another number whose square is 1, namely -1. And so it is a priori not completely clear which of these numbers should be called root of unity. And the convention is that if you have a positive number, its root is just a positive value of a number whose square is a given number. And today we will talk about roots in complex domain, and there is no such unique choice. And so actually even for complex number 1, there are n different complex numbers whose nth power equals to 1, and they are all called roots of unity. So this is the topic for today's lecture, but before we start, I want to spend a few minutes discussing polynomials and their roots in general. And I don't want to prove all the theorems there because they are standard. You will see their proofs in Algebra 2. And also, if you want, you can look up my lectures on linear algebra previous quarter, and they are also online. And there is a lecture about polynomials, and most theorems which I quote now are proven there. But otherwise, you can just believe me that they are correct. So let's start with the definition. So let's suppose we have some polynomial, maybe p of x, and this is a polynomial with coefficients in some field as usual, so it doesn't matter which. So some element in the field is called the root of p. If when you plug it in, you get 0. Very standard. As an example, let me do something slightly less trivial. So for instance, you can take, if you have z power 4 minus 1 equal to 0, so this is exactly this sort of fourth roots of 1. Then you have 4 solutions. You have solution 1, you have solution I, because I squared is -1, I power 4 is 1 again. You have minus I, and you have -1. So it has 4 roots. And another example, let's do, for instance, field with 2 elements, and you can take a polynomial x cubed plus x squared plus x plus 1. And for instance, this one has a root x equal to 1 if you think about a field with 2 elements, because when you plug in 1 here, you get 1 plus 1 plus 1 plus 1, which is 0. So that's the definition, and the natural question is how many roots a polynomial might have. And you know very well that even a boring degree 2 polynomial has at most 2 roots, and there is a formula for those. But if you think that p and q are real numbers and you are looking for a real root, sometimes it has 1 root, sometimes it has no roots. So first, let me maybe mention that. So a polynomial of degree d cannot have more than d roots counted with multiplicity. So here is the idea. So imagine you have a polynomial like x minus a squared times x minus b. So formally speaking, it has 2 roots, a and b. But you see that x minus a comes here in degree 2. So in some sense, you can think that it has a double root. So one way to think about it is that, so if you just open brackets, you will get some degree 3 polynomial, like say x cubed plus p1x squared plus p2x plus P2. And if you move slightly this P1, P2, and P3 numbers just a little bit. Of course, your polynomial will not become a product like that anymore. It will be something like x minus a1, x minus a2, x minus b. So let me draw a picture maybe. So this is a picture. So imagine you have this sort of cubic parabola. And so when it had this double root, this part of the cubic parabola was tangent to the line. So it was something like this. And if you slightly move coefficients, you start to see two roots, and this a1 and a2 are very close to a, so both of them are roughly speaking equal to a. So if you think that your polynomial has one root, it's a little bit misleading. Actually, it has two roots which coincide. And so there is a special notion of multiplicity, which I will define in a second, and the general statement is every polynomial of degree d can have at most d roots if you count them the number of times in which degree it comes inside the polynomial. So definition is as follows. So definition. So p of x has a root x near 0 of multiplicity d if there exists a polynomial q such that q of x equals to x minus x0 power d times q of x. And of course, what might happen is that actually q also have x0 as a root, and then the multiplicity is bigger, so such that q of x0 is not 0. And this is one of the possible definitions, and I will use this one mainly. So if your polynomial has the number of roots counted with multiplicity equals to the degree, so if p has roots, let's say x1 with multiplicity m1, x2 with multiplicity m2, and so on up to xk with multiplicity mk, such that the sum of multiplicities is the maximal possible, x1 plus and so on plus mk just equals to n. So then your polynomial can be very simply written down. So p actually is just a product x minus x1 times power m1 times and so on times x minus xk power mk, maybe times some constant, you never know, which will just give you the leading coefficient of p. And so this very simple presentation exists when it has maximal number of roots possible, equal to the degree, if you count them properly. But sometimes polynomials are not like that. For instance, if you take something like x squared, say, plus x plus 1, and you think of this polynomial as real coefficient polynomial, then it just has no roots. So there is no way to write it down any simpler than that. Of course, it should not surprise you very much that if we start using complex numbers instead of real numbers, this polynomial will have a root. I mean, after all, complex numbers were invented so that there will be a root of unity which you can take. And so if you just look at usual formula for roots of a degree 2 polynomial, you will get something like minus 1 plus minus square root of minus 3 over 2, which is minus 1 minus 1/2 plus minus square root over 3 over 2i, and this is perfectly nice complex number, so suddenly your polynomial has two roots. And this is not surprising at all, because so we invented complex numbers to be able to take roots of negative real numbers, and this is one of those, so it has two roots. Miraculously, over complex numbers, something much stronger is true. Namely, just every polynomial with any complex coefficients is like that. Every polynomial has a number of roots equal to the degree if you count them with multiplicities. So this statement, which we will prove probably next time, I'll try to do it. It's really hard theorem. It's called the fundamental theorem of algebra. I think there are like about 40 proofs which I vaguely heard of, and maybe much more of this beautiful theorem. And though it is so fundamental, it sort of underlines every area, almost every area of mathematics has its own proof of the fundamental theorem of algebra. None of them is simple. And in the early 19th century, there was a big struggle to come up with a correct proof, and D'Alembert wrote, I guess, a first one, which was slightly not complete. And if you have already taken Analysis 1 course where you heard of compactness, stuff like that, this was exactly what he was missing. So there was some compactness argument he was not able at that moment to formalize. And the first complete proof was written by Gauss, and actually Gauss came up with a few proofs. So we will probably discuss a very algebraic proof, which does not use a lot of analysis, but miraculously you cannot prove this theorem by pure algebra. You need some little bit of analysis involved, and we will just use the fact that every odd degree real coefficient polynomial has a real root. This is what we are going to use. But anyways, this will be later. So I just wanted to say that this complex numbers has this miraculous property. Every polynomial is a product of degree 1 monomials in some powers. So what I want to do now, I want to spend a few minutes discussing kind of relation between complex roots and real polynomials, because you are, after all, mostly used to real polynomials, and the question is, okay, is there anything about their complex roots I can say? And after that, we will talk about roots of a very particular, very simple polynomial, namely x power n minus 1. And you know, the theorem predicts it has n roots, and you can actually prove, and this is really easy, it follows from one elementary exercise which will be in the next homework, that multiplicities of roots of this polynomial are all equal to 1. So this m1, m2, and so on, mk, just 1. So basically it should be a product x minus 1, and then, I mean, there should be something else, right? So actually there will be some product of something, which will be called roots of unity. I mean, I can even, yeah, x minus d10 minus 1. I will explain who these guys are. And these are some very interesting complex numbers. And of course they must be special because, I mean, they are, you know, roots of 1. So they play a very special role. And so after we discuss a little bit real valued polynomial, real coefficient polynomials, we will go to the geometry of roots of unity and some of their properties. Okay, so let me go to the next part. Okay, so next part, I want to formulate a few very simple properties of roots. So the first one is the one I already sketched during office hours, which is called Vieta's formulas. So they are very useful and elementary statement. So let's suppose you have a polynomial p of x, and it is a product x minus x1 times and so on times x minus xn. These roots here can repeat, so you can imagine it as any polynomial with n roots counted with multiplicities, or you can imagine p is a polynomial with complex roots, and then such presentation always exists, and I assume that leading coefficient is 1 for simplicity. So it has a presentation like that, but it has another presentation. I can write it as x power n plus a1 x power n minus 1 plus and so on plus a0, as usual. So then the question is how these numbers and these numbers are related, and the answer is very simple. So there is a sequence of formulas then, so which are we just follow by opening brackets, and if you just multiply, just open brackets and look at a coefficient before x power n minus 1, you will get that x1 plus and so on plus xn is minus a1. And if you look at degree n minus 2 polynomial, you need to multiply in two brackets, you need to take x, and in all others you can take constants. And so you will get the statement that some xi xj equals to, so for I less than j, so just all products, equals to A2. And so on, up to the product of all these guys, so x1 times xn equals 2, and then the sign depends on the degree, it's minus 1 power n, A0, sorry, A1, AN. So this is a way to relate roots and coefficients. And you see, so this polynomials and many variables are called symmetric polynomials. They have a name. This is sigma 1, sigma 2 up to sigma n. They have a lot of beautiful properties, and maybe we will come back to them next time, but I'm not sure about that. Let me just kind of leave them here. So there is nothing to prove. You just open brackets, and this is what you get. So this is one thing I will use today, a little bit later. So another thing is the following observation. So again, very simple. So suppose f of x is a polynomial with real coefficients. Then f has a real root. So this is a statement you use analysis to prove. So the proof is very simple. So if you take your polynomial, it has some, leading coefficients, say a power n, x power n plus and so on. Let me say 2n plus 1 because I said it's suppose f of odd degree, 2n plus 1. And up to a0, and then let's suppose that the leading coefficient is positive, because otherwise you just multiply by minus 1. And then you can notice that the limit when x goes to minus infinity, f of x is minus infinity, and limit when x goes to infinity of f of x is plus infinity. So your polynomial actually looks like this, but it starts at minus infinity and goes to plus infinity, doing some swings. And then by intermediate value theorem, so by intermediate value theorem, f has a root, just because this function is continuous. Somewhere here. So this is a statement I will need later on, and I just proved it to you, so proof is very simple. Finally, let's suppose that f of x is a polynomial with real coefficients, and z in C is a root. So I said in the definition of a root that you look at a polynomial with coefficients in a field and you look at an element in a field, but of course nobody can restrict you from taking an element in a field which is bigger, say complex numbers instead, and plug in a complex number inside a polynomial with real coefficients. You still know how to do that. You can think reals are just special complex numbers. So then z bar is also a root, and you can say of the same multiplicity. So basically, if you have a real polynomial with real coefficients, complex roots go in pairs, z bar. So why? The proof is very simple, because imagine you have your polynomial f of x equal to again a n x power n plus td plus a0, and then if you take f of z bar, this is this a n z power n plus td plus a0 bar. But remember, when you do complex conjugation, it sends sum to sum, product to product, power to power, and so you just get a n bar z bar power n plus td plus a0 bar. But when you conjugate real numbers, you get your real numbers back. So this is just a n z bar power n plus and so on plus a0. So this is just f of z bar. And so if your polynomial had a root, z, then z bar will be also a root. And if your polynomial is presented as a product, it's easy to see that both, so if your polynomial f of z equals to x minus z power n times some other polynomial q of z. Then you apply the same idea and you get that f of z bar equals to x minus z bar power n times q of z bar, and whatever this is, sorry, q of x, whatever that is, it is some polynomial. So of course z bar will be a root of the same multiplicity. So example, so if you take your favorite x squared plus px plus q polynomial and you take a root minus p plus square root of p squared minus 4q over 2, then you might notice that, so if, imagine that this thing is negative, the discriminant is negative. So then actually there are two roots, plus and minus, and they are exactly conjugated because this will be a negative real number. So this will be I times a positive real number, and so switching sign is exactly switching sign before I. And so a polynomial with real coefficients of degree 2 is either has two different real roots, like x minus a times x minus b, or maybe x minus a squared, which is just double root, or it is a product x minus z times x minus z bar for some complex number z and its conjugate. So there are three options. You cannot have x minus z times x minus w for two unrelated complex numbers. It will not have real coefficients. So these are like several little statements I wanted to go through before we start talking about roots of unity. Last thing, yeah, so I can say a corollary of the statement. So you have a polynomial of even degree with real coefficients. It will have even number of real roots and some number of pairs of complex roots. If you have a polynomial with of odd degree, it will have odd number of real roots and a bunch of pairs of complex roots, complex and complex conjugate. So this is already very useful for many purposes, and in particular, remember I formulated this fundamental theorem of algebra that a polynomial is a product of monomials. But now you can group x minus z and x minus z bar terms, and you get that a real polynomial with real coefficient is a product of monomials x minus a and quadratic polynomials of degree 2 with complex conjugate coefficients, roots, sorry. And this is a real version of fundamental theorem of algebra, which I will maybe formulate when I talk about fundamental theorem of algebra in detail. Okay, so next topic is actually roots of unity. Okay, roots of unity. So before we even start, let's just look at some examples. So, okay, x minus 1, just one root, 1, boring. X squared minus 1, x minus 1 times x plus 1. Not very interesting either, but these are two roots of unity. Let me also draw them. So this is 1 in complex plane, and these are minus 1 and 1. So, okay, cubic equation, that's the first interesting case. So of course I can write it down as x minus 1 times x squared plus x plus 1. And for the second part, we already found the root. So it is x minus 1 times x minus 1 plus square root of minus 3 over 2 times x minus 1 minus square root of minus 3 over 2. So I can draw it approximately very easily. So that's something like this. And let me call this number zeta 3. This will be zeta 3. This is 1, that is zeta 3. So let's look at this picture for a second. So this is an interesting number because you recognize minus 1/2 square root of minus 3 over 2. So zeta 3 let's write it in trigonometric form for better interpretation. So minus 1/2 is cosine of what? So, you know, that's cosine of something nice. So it's probably something like 2 pi over 3, I guess, right? Plus I sine 2 pi over 3. And this is just this number. And notice it's very interesting. So this angle is exactly 120 degrees. And then you know that, as we discussed, if you have a real polynomial, roots should be complex conjugate to each other. So the other one is zeta 3 bar. And so it equals to the same thing minus, but if you can just rewrite it as cosine 4 pi over 3 plus I sine 4 pi over 3. And so this is also 120, this is 120, and your roots of unity are vertices of a regular triangle, which is, I think, a very beautiful observation. So another way to think about it, so we know that if you multiply complex numbers, then their absolute values multiply, their arguments add. And so absolute value of this root of unity is also 1. Of course, if you have just any roots of unity, x power n equals to 1, then you can look at absolute value and you get that absolute value of x times 1 equals 1. And now this is a positive number, so definitely absolute value of x equals to 1. And so all of them have absolute value 1. And also you know that the argument, the angle, is twice bigger because it's 240. So this means that this is just zeta 3 squared. And this is something you might not notice if you look at these numbers, that if you square up this guy, you get this one. But this is indeed true. So another way to see it is that if you take, you know, if you have x such that x squared plus x plus 1 equals 0, if you instead look at x squared, you will get x power 4 plus x squared plus 1 equals 2, and then you can simplify, you know, x cubed is 1, so it is x plus x squared plus 1, so also 0. And in this way you get that actually roots of unity of degree 3 are 1 something, something squared. Okay, so I already told you that for x power 4 minus 1, the picture is like that. I1 minus 1 minus I, and you have a regular foregone. And hopefully now you see the pattern. Pattern is very clear. So what happens in general is that roots of unity actually form vertices of a regular n-gon. That's the picture. And they are just 1, some root of unity, it's square up to zeta, and minus 1, and roots of unity. So let me prove that and formulate that and explain that. So the easiest way is just, you know, to find them explicitly. So suppose we are trying to solve equation x power n equals to 1. So then we can just, you know, write x in some way, like r cosine phi plus I sine phi. And then we know that r power n equals to 1, so r equals to 1, and that's just this argument. And then we know that cosine n phi plus I sine n phi equals to 1. And when it equals to 1, it means, sorry, n phi, it means that n phi is a multiple of 2 pi k, for some k, and this is n phi is 2 pi k, and then this will be satisfied. Because cosine of 0 is 1, sine of 0 is 0, and that's the only solution. So actually, such phi's are just all numbers of type 2 pi k over n, but remember, if you take your argument and add 2 pi, you will get the same complex number, so you do it modulo 2 pi. And if k equals to n, then you will get exactly 2 pi, and then this will start to repeat. So actually phi is just element of a set 0, 2 pi over n, 4 pi over n, up to n minus 1 pi times 2 pi over n, and this is exactly n roots, so as much as we can possibly hope for, because degree is n. And these things are exactly arguments of roots of unity. So let's take the one which has the smallest argument. So let zeta be equal to cosine 2 pi over n plus I sine 2 pi over n. So it has another expression. You can just write it down as e power 2 pi I over n. And this is probably the most convenient notation for root of unity. So obviously zeta power n in this notation is just trivial, is e power 2 pi I over n power n, is e power 2 pi I is 1. And so this is a root of unity. And then my claim is that for every k less or equals than n minus 1, greater or equals than 0, zeta power k is a root of unity. And again, I already proved that, to be honest, but let me just double check. So of course, zeta k power n is the same as zeta n power k, which is 1. So that's why. And these things are all distinct, and they are distinct. And this follows from the fact that we just look at them and they have different arguments, so that's why they are distinct. So this is what the roots of unity look like. They are vertices of a regular polygon, and they are these powers of the simplest of those, which is just cosine 2 pi over n plus I sine 2 pi over n. What else do I want to say? So of course I can just rewrite it, saying that x power n minus 1 is equal to x minus 1 times x minus zeta times x minus zeta squared times and so on times x minus zeta power n minus 1. And I can get a lot of corollaries. For instance, I can compute some things, like I can prove that from here it is obvious that 1 plus zeta squared plus and so on plus zeta n minus 1 is 0, just from Vieta's formulas. So you can just use it, you prove it by saying that this is zeta n minus 1 over zeta minus 1, which is 0, and so on. So you can derive a lot of things about roots of unity. And maybe another way to think about it is that if you take a rotation by angle 2 pi over n around 0, so this transformation we discussed last time, it is just a transformation sending z to z power z times zeta. So you just multiply your complex number on root of unity, and this is a rotation of your plane by this angle 2 pi over n. Okay, so there will be a lot of problems about roots of unity in the next homework, and there will be an interesting notion of a primitive roots of unity. This is the one whose powers generate everything. And let me leave that as for the exercises. So maybe last thing I want to mention is that roots of unity form a group. So remember, a group is a structure where there is an operation and you can multiply, there is an inverse, and there is a unity. So let me now explain here what I mean by that. Form a group. So the notation is nu n. And this is just this group, and as an element that has just this n minus 1 elements, and otherwise you can say that this is z inside C, such that z power n equals to 1. And why it is a group? The operation is usual multiplication. So if z1 is in nu n, z1 and z2 are in nu n, then you know that z1 power n is 1, z2 power n is 1, and then you can just multiply them. So z1, z2 power n is 1. And then if z power n equals to 1, then you can take the inverse. 1 over z power n is 1. And finally, there is 1. So 1 power n is 1. And so all axioms of a group are satisfied. So this is a group, and actually this group has a very simple structure. So you can think of these elements, they are in bijection with all remainders of integer numbers modulo n. And the way they are multiplied is you just, if you have z power a times z power b, so the product is z power a plus b, but this is the same as z power a plus b mod n. So you can just take the remainder modulo n, and the power will be the same because zeta power n is 1. So actually this is just a copy of a group which are just remainders modulo n. And so this is not that maybe complicated group after all. So still roots of unity has interesting properties, and partially because if you take, for instance, six roots of unity, if you take any 6 roots of unity and some zeta here, and if you look at zeta squared, this will be actually a third root of unity, because if you take degree 3 of it, you will get 1. And if you take zeta cube, you will get degree 2 root of unity, so it's plus minus 1. And probably from here the interesting structure of roots of unity comes from, and there will be some exercise and homework to look at that. Okay, so let me end this lecture here, and next time we will go to fundamental theorem of algebra, and after that to Möbius transformations and fractional linear transformations of complex plane. Я все.